Okay? Now let me present you a far more interesting case study. This is a disaster, one of the worst engineering structural disaster that happened in '81 in Kansas City, Missouri. Some of you may have probably seen this in, maybe some documentaries on Discovery Channel or someplace else. The Hyatt Regency Hotel had opened only a year before the disaster happened. And Hyatt Regencies, they have a very unique atrium design. So they had these skyways basically hanging above the main lobby. They were hanging from the ceiling. They had an upper skyway. It was glass, so people could actually walk on the upper skyway, on the lower skyway, and then, of course, you had the floor. So when the disaster happened, people were having party. I think there was some tea party going on. There were a lot of people on the ground floor dancing, people walking, enjoying the party from the upper skyways, the lower skyways, and then something happened. People heard a noise, some sort of popping noise, cracking noise, and the whole structure came down. 114 people died. 185 people were injured. Of course, when this happened, people wanted to know what happened. Was it a problem with the design? Was it a problem with how the things were put together when they were constructed? So there is a small YouTube video. In fact, there are quite a few, but I found one that I thought was a little bit more relevant. So I want to play that so you can see exactly sort of a recreation of what happened. And once we have seen that, we will see it based on what we have learned so far in this class with the free body diagram and equilibrium analysis, we can actually tell. Beneath the walkways, people are totally unaware of the danger presented. 7:04 p.m. 1 minute to disaster. Chilean water trooper joined a crowd on the first floor walkway. Seconds later, a base of approximately 9 UV droplets. As its ground snap, people hear a popping from up to 30 meters away. As the base of the beam folds, clear on, rip free. As the restraining nut smashes into the top of the beam above with a sharp crack, the walkways drill down, sharp. 2 seconds later, disaster strikes. Box beam 9 UV fails. To find the remaining connections on the third floor instantaneously unzipped. The third floor walkway flies down at over 15 meters per second. 65 tons of concrete steel crash into the lobby floor in just 1.6 seconds. Okay, so the point to notice from that video was that there was a nut and there was a box beam, and box beam basically opened up, right? So why did that happen? That was the main problem. So this is how it was designed, right? What you're seeing on the left. This is how the walkway was designed by the design engineers. This is how it was actually built. So now if you look at those two designs, maybe some of you can tell the difference, right? But even if you cannot tell the difference, based on what we have learned about free body diagram and equilibrium analysis, using those two concepts, we can tell exactly what the problem was with the walkway as it was built. It turns out there was no problem with the walkway as it was designed. Now, if you notice the difference, clearly the difference is that here you have on the left-hand side in the original design, you have one single monolithic rod that runs from the ceiling to the bottom, right? And on those two rods, you have the nuts that are tightened. So, of course, you have to have threads here as well as over here. And then you had the skyway supported on those nuts, right? And the box beam that basically buckled, that opened up, was right over here between the nut and the skyway, right? But that's not important because we want to see what is happening with the nuts over here. So this is how it was designed. One rod running from the ceiling to the bottom. But eventually, when it was put together, the guys who were responsible for putting this together, the contractors, they probably had a better idea. They thought, hey, why try to acquire these really long rods that run into 60, 70 feet when we can get shorter rods that are easier to handle, carry, right? And we can install them much more easily. So they put basically 2 rods instead of 1 rod, right? So 2 rod became essentially 4 rods over here. Another reason that is not mentioned in your textbook, which I know, is that if you look at this design, right, we know that wherever the nuts are, that's where the threads have to be. Okay? Now, when you cut the thread, the effective diameter at where the threads are cut would be less, right? You have to pass this nut, which has to fit the thread, which means that the diameter over here of the rod would have to be smaller too. So the design engineers, the guys who designed this, they basically ordered about 20 feet of thread to be cut from here to here, right from the lowest nut to the middle nut, so that you could push the nut up. If you don't have threads over here, how are you going to push the nut to the middle? Of course, that's a lot of cost, right? You have to thread this 20 feet of rod, both of them. So the contractors who were putting this together said, hey, if we use 2 shorter rods, we don't have to cut 20 feet of thread. We can just push the nut from the top, from the ends, and that'll solve the problem, right? So this is what they did. Okay. So let's try to do the analysis and see if we can figure out what the problem is. So this is our walkway as designed, right? So what we'll do is we'll draw the free body diagram of everything in here. And we'll see what sort of forces we have, right? And then we'll do the same with the walkway as it was built and compare the forces and see if we can tell what went wrong, right? So let's start with the lower skyway. So I'm going to start with free body diagram of lower skyway. So I'm going to draw the lower skyway all by itself, nothing else, right? Let's assume there is some weight, and let's not worry about the people and all that weight, right? Just the weight of the skyways. So let's say the weight of the lower skyway is W, okay? Then the lower skyway is supported on 2 nuts at the end, so the nuts have to apply reaction force in the upward direction, so let's call them P1. And since this whole thing is symmetric, there is no reason to assume that P1, that the 2 end reactions are going to be any different from each other. So let's just assume they are both P1. So if you do the analysis on this, we can see that 2P1 should be equal to W. If this is an equilibrium, then all the forces have to be balanced. So all the upward direction forces should be same as all the downward direction forces. And that gives us P1 to be equal to W by 2. Right? No problem. Okay. Now let's look at the upper skyway. So free body diagram of upper skyway. And for simplicity, let's assume that the weight of the upper skyway is also W. It doesn't have to be, you could do the analysis with a different weight, but let's just assume it's also W, okay? All right, now upper skyway is also supported on 2 end nuts. So let's say these 2 forces are P2, okay? Any other forces on the upper skyway? That's it, right? These are the only 2 forces. So again, we get P2 to be equal to W by 2. So it turns out that with this, if let's say you assume that lower skyway and upper skyway are of the same weight, then the 2 end nuts for each skyway are supporting half of that weight. Right? Okay, so that's good. So now let's talk about the rods, right? Because maybe the rods were the failure point. We don't know that. Now, you've already seen in the video as well as in my previous slide that it was the outer nuts that were the point of failure. But, let's say we didn't know that beforehand and we wanted to do a full-fledged analysis to see maybe it was the rods that actually, stretched beyond a certain point or they fractured or something like that. So we want to see what happens with the rods also. Okay, so let's see. So what we'll do is we will make a cut here, right? Because we want to see what are the forces at a cross-section between the upper and lower skyway, right? So if I do that, so I'm going to call it a free body diagram of lower part of the rod. So what do I have? I made this cut, right over here, okay? So now the lower skyway, which is right over here, is also going to push the nut in the downward direction with the force P1, right? Because you have this nut over here. So this is pushing the nut down with the force P1, Newton's third law. This is P1 up, this is P1 down, right? The same force that the nut is applying on the lower skyway is the force that lower skyway is applying on the nut in the downward direction. So we have that. And if this rod is to be in balance, then the force in that cross section should be P1 too, right? And we already seen P1 is W by 2, so both of these are W by 2, right? Okay. What about upper part of the rod? So let's say I'm going to make a cut here like that. So I'm going to create this cross section. So now I have free body diagram of upper part of the rod. So I have this, then I have my nut right in the middle, and then I have another cut, right? We just found this force is P1, and that's P1 like that. We've also seen that this force is P2 on the nut in the downward direction, like that, right? The nut that is supporting upper skyway is being pushed on with the force P2. So what this force would be, let's call it P3. P3 should be equal to P1 plus P2 from equilibrium analysis. P1 and P2 are W by 2, so this is actually W, right? So if you make a cut in the upper part of the rod, above the upper skyway, below the ceiling, the force is actually W, but in the lower part of the rod, it's only half, right? It's only W by 2. Okay, so this is a scenario with how it was designed, and I'm pretty sure that the guys who designed this did exactly this kind of analysis, drew the free body diagram, and calculated the forces that would be acting at different points, right? So if you had the box beam, which is not shown over here, that you saw in the video, that was right above the nut, then the box beam is being compressed by the nut and the upper skyway by the same force W by 2, right? The same force W by 2. Now, think about it, if that's it, let's say that force increased by any factor, then the box beam could buckle because they are under compression, right? So let's see what happens with the walkway as it was built. Okay, so we'll start with the lower skyway like we did before. So let me just call it lower skyway, LS. Same weight W, the force P1, 2P1 equal to W, so P1 is half of W, same as before, no changes, right? So nothing changes with the lower skyway. The load on the nuts on the lower skyway is also same, right, as before, W by 2. Let's see what happens with the upper skyway. Weight W, right? Now, what is the force from these nuts on the upper skyway? It'll be P1, right? Because if you look at the free body diagram of this rod, this whole rod, what do you have? You have the nut, you have the rod, then again the nut, right? So this is being pushed on by force P1. That means this should be pushed up by force P1 too for the whole thing to be in equilibrium, right? Same forces. So which means that the forces from these nuts on the upper skyways are P1 too, right? Okay. And then you have these nuts, the outer nuts, which are also supporting the upper skyway. So that means these nuts will be applying an upward direction force on the upper skyway. Let's say that is P2. And I'm using the same symbol as I used in the previous slide, but remember, they are not same numbers, right? I'm just using, I could have put prime everywhere, but it will just make it messy. So I'm just using the same symbol, but remember, the numbers could be different. So these are all the forces of the upper skyway. So if you do the equilibrium analysis, upward direction forces are 2P2, and that should be equal to all the downward direction forces, which is 2P1 plus W. So what do we get? We get P2 equal to 2P2 equal to 2P1 plus W. And what is W? W is equal to 2P1, right, from here. W is 2P1. So what do we get? We get P2 equal to 2P1. And what's P1? 2W by 2, so that's basically W. Something has changed. Now the force on the outer nuts is W, right, while it was only W by 2 in the previous case. So by changing one rod design to a two rod design like this, essentially you have doubled the load on the outer nuts. Now it will turn out, if we do the analysis further, that the forces in the rods actually don't change. The forces in the rod will be exactly the same, both the lower part as well as the upper part of the rod. Now here you have two different rods, so you can compute the forces in each section. So clearly here the force is going to be same as P1. Here the force is going to be P2, and P2 is only half of W. So P2 is actually W, so the same as before. So everything else remains same except for the load on the outer nuts. The nuts have to take now twice the load, and that's what went wrong. and that's why the box being buckled. Right? Now, there is something seriously wrong with this, right? Not to mention that, you have an obvious flaw. Nobody did this kind of force free body diagram and equilibrium analysis, right? I mean, you guys in Mech 101 class, you just learned this. You could have done this based on your knowledge from the last 2 classes, if only you were asked to, right? But there is something more sinister going on with this. What is really wrong is that even if, let's say, this was put together like this, it should not have failed. Do you know why? Anybody wants to guess? Because the original design was stronger than it needed to be? Well, that could be true. I mean, it could be over-engineered, but that doesn't answer the question as to why this should fail. If it was over-engineered, then it should not have failed at all, right? Are you saying that it should have been over-engineered? Is that what you're trying to say?
I mean, I was suggesting that it might have been
under-engineered?
No, I was suggesting that it might have been built stronger
Than it needed to be?
the exact amount it needed to be for safety reasons.
Could be.
I think because of the thread cut, like it has less thread cut than the other one, so the nut will just like fall away.
But that was not the reason. The thread is sufficient to keep the nut in place. You don't really need the whole rod to be threaded, essentially.
The upper rod should have been made thinner because they were separated into 2 separate rods instead of one whole system.
But the rods were clearly not the problem. We just learned that.
Shearing moments?
The shearing moment,
Yeah, between the 2 forces, the 2 opposing forces.
the shearing forces, where would you see the shearing forces? Everything over here is in tension, right? The rods are in tension.
You have tension pulling upwards and a tension pulling downward.
Right.
There's a shear between them.
Okay, it's shear between them. But I think maybe I have not phrased my question correctly. What I'm really asking is, what I'm saying is that despite this double the load, this structure should not have failed if something else was taken into account. And that's what I'm looking for from somebody.
I would say it's the safety factor of the material.
Exactly. It's a factor of safety. Pretty much with any structure, any machine, any part that is designed out there, there has to be a factor of safety. How many times you guys have stepped into an elevator and seen this label saying that rated for, 10 people, right? Rated for 10 people. What does that really mean? So let's say we assume that on average a person has mass of 75 kilograms. So does it mean that that elevator is designed for 750 kilogram of load only?
That's sort of what I was trying to say earlier. You can put more than 10 people in there,
Right.
but you probably shouldn't.
Right. So I got that. So essentially what you were trying to say was that there should have been some factor of safety built into the system that could have prevented this disaster. So imagine even if it was like a single rod, right, just as it was originally designed, and if you put like more people now on the upper skyway or lower skyway, should it fail? Well, it all depends on what your factor of safety is. So when you step into that elevator, if it says it's rated for 10 people, elevators have to have factor of safety of something like 6 to 10. That means it's actually designed for much more than that. Wherever people are involved, the factor of safeties are very large. Okay? This doesn't even have a factor of safety of 2. And people are going to be walking on the structure. So it doesn't even have a factor of safety of 2, which is completely unheard of. So this is a design problem too then in that sense, right? That it couldn't take factor of safety. So it's not just the guys who actually put this together who are to be blamed, but even the design guys, because there's practically no factor of safety with this thing. Right? Now, there are certain areas where you cannot have very large factor of safety despite human beings involved. Can you think of any scenario like that? Aircrafts. Weight is at a premium. Jet fuel is expensive. So the aircraft companies are trying to reduce the weight as much as they can. That's why you have to pay for that extra bag when you travel these days, right? So that's why they're trying to design the material, using composites, changing the geometry, doing the topology optimization to make the structure as lightweight as possible without sacrificing the strength. Right? So, but based on what we have done, this is something that we could analyze and see where the problem would be.